Hi, everyone. My name is Yutaro. I'm a research scientist at Sakana AI. And today I'm going to be talking about the AI Scientist-v2 workshop-level automated scientific discovery via Agentic research. This is a joint work with Robert Lang, Zhong Liu, Sharon Hu, Chris Liu, Jacob Forrester, and Jeff Clune and David Ha. So to set up the scene, I kind of want to step back and reflect on what we've seen in the last decade, especially in the field of generative AI technologies. So if you look at the image domain, we started from VAEs and GANs, and now we have diffusion models that can produce really realistic images. And if you look at the text domain, we started with sig to sig, and then transformer came, and now we have these large language models from frontier labs that can do a lot of interesting and complex reasoning. And for the video domain, especially in the last 2-3 years, I think, we also saw tremendous progress in the video quality. And now we have things like Sora 2 or Veo 3 that can produce hyper-realistic videos. And for the science domain, in 2021, we saw AlphaFold, which basically predicts the 3D structure of a protein based on amino acid sequences. And this achievement just got a Nobel Prize in chemistry last year. And this ESM3 is sort of similar to AlphaFold, but also predicts the functions of proteins, which sort of goes beyond just the 3D structure prediction. And these are sort of really great progress, but these are sort of automating parts of research. And what we wanted to ask was, if it's even possible to automate the entire process of scientific research. And AI Scientist v1 was sort of our first attempt towards this goal. And this was released in August of 2024. But I think we think this is sort of still the beginning of something bigger. And as we saw in the image domain, text domain, and video domain, we would expect more improvement over time in this automated science domain as well. And also, as we saw in these other fields, collective effort from open source communities would be critical. So large language models, or LLMs, have already been used to automate parts of scientific research, or machine learning research especially. And this often comes with evolutionary search style algorithms, where LLMs are used to generate candidate solutions and evaluate them based on some sort of fitness scores, and update the library of these candidate solutions. And this loop sort of continuously goes on to design novel solutions. And this has many applications, such as designing loss functions in machine learning, and also for reinforcement learning can be used to design reward functions, and things like neural architecture as well. And you can even go a little bit of meta by thinking about designing LLM agents itself by using this sort of evolutionary search style algorithms. But science is not just the discovery of individual components. It ranges from discussing ideas or problem even identifications, and thinking about hypotheses that could make sense with colleagues, and brainstorming, and actually running the experiments based on your hypothesis. And once you have some nice results, you might consider writing a paper, and then that goes through reviewing, and then back and forth with reviewers, and eventually might get published, and the knowledge sort of disseminates across the internet through blogging or social medias. So the question, again, we wanted to ask was, can we automate this entire scientific research process from idea generation, running experiments, and writing papers with some sort of AI systems? So the grand vision here is that these AI scientists can then accumulate their discovered knowledge and then continue innovating almost endlessly, just like how the human scientists or human scientific communities do. And so this AI Scientist-v2 was our first attempt. And this is sort of like an overview of the pipeline of AI Scientist-v2, which was template-based, and template-based in a sense that it had to rely on like human-authored code or code templates that was provided at the beginning, sort of like as a seed. And this pipeline has 3 stages, like from idea generation, experiment iteration, and paper write-up. But all of these stages was sort of a condition on the provided code template. So for example, in the idea generation stage, all these generated ideas were sort of like derived from the idea that was presented in the code template. And for the paper write-up back then, we didn't really have a reasoning model like O1, so we relied on like a section by section writing with incremental edits. So to evaluate the system, we chose 3 distinct subfields of machine learning, from 2D diffusion modeling, NanoGPT, which is sort of like a mini library for training small transformer-style language modeling or models, and grokking, which is sort of like an interesting phenomenon in machine learning, where if you continuously train on the training data set, even if you reach like 100% accuracy on the train set, if you like sort of continue, suddenly like the model kind of groks the idea behind data generating functions, and then the test performance sort of goes up, which shows an interesting like generalization capability. So here's an overview of the performance of the AI Scientist-v2. We generated about 50 papers in each of the subdomains we chose using 4 different frontier models. We see that the Sonnet 3.5 performs the best, and Llama 3.1, which was about 400 billion parameter model, performs the worst. So what's interesting here is like the DeepSeek model, which is an open source LLM, also performs relatively well in this scaffolding compared to Sonnet 3.5 and GPT-4o. But there are several limitations in the V1 system. And most notably, as I was alluding to, we had to rely on human-authored code templates. And also the execution plan was sort of like linear in a sense that it only tracks like a single chain of operations of improving and debugging. And the system didn't really support like parallel executions in the experiments, and we didn't use vision language models or VLM anywhere in the pipeline. And so in the V2 system, we try to sort of address these weaknesses that were there in the V1. And here's an overview of the pipeline of the AI Scientist-v2. It's very similar to V1, but we try to generalize sort of like every stage from idea generation, which uses more sort of like a grand proposal style idea generation now. Experimentation part uses tree search, which I'm going to go into details more in the next slide. And the paper write-up is now using more powerful reasoning model, so that we don't need to rely on like section by section writing. And it kind of one-shot generates the idea of data paper. Yeah. So yeah, let's now dive into how AI Scientist-v2 conducts experiments. So unlike V1's linear approach, V2 uses a multi-stage sort of like tree-based search. This was inspired by methods like AID. And we introduced this experiment progress manager that kind of guides the research through 4 distinct stages. The first stage is a preliminary investigation to get a working prototype, basically. The second stage is a hyperparameter tuning for a robust baseline. And third is this executing, this is basically the most interesting part, which executes the main research agenda that was from the idea markdown. And finally, conducting ablation studies for rigor. So the core of this is the agentic tree search. And in this tree, each node represents an experiment attempt. This contains like the plan or the generated code and numerical results after running the experiment, and error logs if there is any, visualization, and VLM feedback on those visuals. So the system sort of explores this tree in parallel. It balances fixing buggy nodes and exploring promising non-buggy nodes using a best first strategy guided by an LLM evaluator. So specialized nodes handle specific tasks like hyperparameter sweeps, ablations, running replications for statistics, and aggregating results. So this structured yet flexible approach allows for more much deeper and more organized exploration than the linear approach of the V1 system. So does the automated pipeline that we presented actually work? To test it, we put the AI Scientist-v2 system to sort of like the ultimate test, which is this peer review process that human scientists also go through. So this is a snapshot of a paper that was entirely generated by the AI Scientist-v2. We submitted this along with 2 other AI-generated papers to one of the ICLR 2025 workshops. So this specific paper received scores of 6, 6, and 7, which corresponds to 2-week accepts and 1 accept, averaging about 6.33. And this score was high enough to surpass the acceptance threshold, placing it roughly like in the top 45% of all submissions, where about 70% of all papers were accepted at this workshop. So to conduct this peer review experiment, we maintain full transparency with the ICLR leadership, as well as the organizers of the workshop that we submitted, called I Can't Believe It's No Better, Challenges in Applied Deep Learning. And crucially, so basically, yeah, the organizers and the leadership knew that we were running this experiment. And then crucially, the review process was blind, meaning that reviewers were informed beforehand that some submissions might be AI generated, but they didn't know which ones, basically. And they could also choose not to review any potentially AI generated papers. And we obtained IRB approval from the University of British Columbia to run this experiment, because this involves some amount of human deception. And we also had a pre-agreed plan that any accepted AI-generated paper would be automatically withdrawn from the workshop after the review process, but before sort of like putting it online or publication. This was to avoid setting a precedent, sort of like without broader community discussion. So this allowed us to assess like the AI's output quality using the standard peer review process. So while the acceptance of an AI-generated paper is a milestone, it's important to stay realistic about the system's limitations and its capabilities. Just like in any other LLM, there is an issue of hallucination. We observed instances where basically this AI Scientist-v2 system generated inaccurate citations, referencing papers incorrectly or missing key prior work. An example is like citing Goodfellow for LSTM, and that's sort of like I think a lot of human scientists would agree that we don't want to make that kind of mistake. And another challenge relates to like limitations stemming from the underlying model's reasoning abilities, which leads to lack of deep sort of like methodological rigor or misrepresentation of results. So for example, in the papers that were not accepted, our internal analysis found cases where a paper sort of discussed the results that weren't actually in the paper, but were in the results, like the experimental results folder of experiment logs. So these examples show that the system can still make errors in reasoning, interpretation, and adhering faithfully to the generated experimental evidence, which sort of reflects ongoing challenges in this complex reasoning by LLMs. So beyond specific errors, let's now consider the broader challenges we might face as a community, because developing these powerful AI scientist-related technologies could bring important considerations. First, for example, transparency and attribution. I think we need to sort of develop some sort of norms regarding AI-generated science, including when and how to declare a paper was fully or partially AI-generated, and at what point in the process of publication. We believe in providing full transparency, or as much transparency as possible, regarding what is AI-generated, but there are difficult questions about whether the science should be judged on its own merit, first to avoid bias against the use of AI. Second is the misuse of these types of AI technologies. We can imagine a situation where systems could be sort of exploited, just to purely game the peer review process to inflate or to inflate publication records. So responsible development requires open discussion about these issues, and establishing community norms and focusing on how these tools can genuinely advance science rather than automating publications. And some people might say, all these issues we just discussed might be overstated, but here are two interesting plots that might be worth discussing. So on the left, we have the plot from Meter, which plots the lengths of tasks AI can do versus model release date. And the main claim here is basically that the length of tasks that AI can do is doubling every 7 months. And on the right, it's a plot, but the y-axis is the sort of AI reviewer score following the NeurIPS score guidelines versus the model release dates. And we can also see sort of a similar or steady increase here as well. So I think there is some evidence that the issues we discussed in the previous slide might arrive sooner than some people might think, although of course this could plateau at some point. So looking ahead, where do we go from here? The long-term vision is very ambitious, which is that AI systems, that can generate research matching or even exceeding human quality at the highest levels. But as an intermediate goal, reliable replication of existing findings from the existing literature would be, I think, a good intermediate goal. And one example here is this paper bench, which is sort of this replication benchmark from OpenAI. And one, I think, intriguing direction to consider is this idea of AI conference, which is a venue where AI-generated papers are submitted and reviewed by AI reviewers and discussed. And this is sort of a system where it has multiple generations of these conferences, and these AI scientists are working together to sort of pushing the boundaries of discourse and knowledge accumulation. And so, yeah, of course, ultimately, the measure of success won't just be, whether AI can do science, but whether AI-driven science helps humanity flourish. And I think we're excited to contribute to that journey. And we've open sourced the AI Scientist-v2 code and the workshop experiment data. And we welcome contributions from the open source communities. And my contact information is here, and feel free to email me if there's any questions here as well. Okay, so thank you.
Thank you, Yutaro. Do we have any questions? Go ahead.
So I have a question regarding experimentation. So for the AI systems, the AI models that are trained today, we have the knowledge that we humans have infused into them. To push the bound of scientific research, we will be thinking about newer things, to push the bound of what we have done today and how to make it better or innovate it in any way possible.
Right.
In your experimentation, do you see any of those things happening in terms of we use that to make it better? Please repeat the question. Anything about those things?
Yeah, so the question was basically LLM already has like a knowledge of scientific discoveries that happen so far, but in order to make like new discoveries and new innovations, kind of has to go beyond that knowledge boundary. And the question was if there was any evidence of that while conducting this experiment. And so I think the sort of like the idea generation part, at least in the V1 and the V2, had a literature search component that tries to basically deviate from the existing literature findings. So based on some concept or based on some initial idea generation, we do literature search so that it doesn't sort of like overlap with the existing findings. So that was sort of like a first, I guess, filter to push the system to find sort of like a more novel findings or discoveries or potential ideas. But I think I guess to push the boundaries more, I think what would be interesting is to have a system where basically it accumulates its own findings as well, not just from the literature search, where it kind of has this database where it sort of like accumulates experimental findings from different branches or different trees, and sort of like it's in an open-ended way to discover something. It's almost like a novelty search to do that sort of to push the boundaries. And I think that that's something that we are interested in exploring as well. Thank you.
Just on the point about coming up with methodologies and as part of the scientific process. If you've evaluated, I'm thinking specifically of molecular bio, like when through the generation process, there's a candidate that comes up, like a protein candidate or a therapeutic compound, to introduce as a steering mechanism more deterministic systems for simulation to steer the plausibility of the research. So you don't end up, with like a compound that's not, physically viable. Like, could you use, computational chemistry, like a function calling, at a meta level, if you like looked into that?
So I personally haven't looked into the sort of domain, but I agree with that. In order to sort of reduce the potential candidate solutions, that it's important to have some sort of like fitness score functions that can guide the exploration to basically towards something more promising than rather than spending a lot of compute or human resources on like unpromising ideas.
Thanks.
Hi, great talk. Thank you. I have a question with regard to the tree search process. And in the stage 2, you say that there is a hyperparameter fine-tuning. And I'm curious about some details about how you evaluate the results and what type of fine-tuning you do, because automated fine-tuning is also very challenging. So yeah, I would like to know more about that. Thank you.
Yeah, so for the stage 2 in the experiments pipeline, there was a hyperparameter stage. And for those, we asked first LLM to come up with a set of hyperparameters that should be tuned. And we basically run, say, n number of hyperparameter tune nodes, or we generate this number of nodes to tune this to tune this hyperparameter, and the evaluation was based on the number of numerical results that were sort of like provided by the code itself. And so this part was automatic, but yes, I do agree that the sort of like the evaluation scheme, or like the choice of hyperparameter isn't as rigorous as it could be, as like the human scientists would do. So this is something that could be improved as well in the future.
Thank you. This is super interesting. I was wondering if, kind of through the process of developing this, if you've looked into the question of using existing scientific research to create kind of reinforcement learning problems with the ground truth, and basically building different agents using reinforcement learning and that data for various scientific applications.
You mean like using basically, the objective would be to discover something novel in using some sort of reinforcement signals, or?
Yeah, but essentially, I'm thinking about the second step of fine-tuning. Can we use the existing kind of corpus of scientific literature to create reinforcement learning data sets and train different versions of models on those reinforcement learning data sets to improve the accuracy of, to improve the accuracy of the model for different problems and applications?
Yeah, I think so. Especially for like scoring these experimental results, reviewing, or like this AI review, like the quality of these AI reviewers are sort of important for both guiding the search of the tree, but also basically improve the quality of the entire the process as well. And I do remember there was some a team. Researchers who had to basically try to improve the AI reviewer using basically using like a data sets that they collected to do some, and then they run some sort of post training of existing LLMs to have a better sort of like a judge, like LLM as a judge scheme to use some sort of reinforcement learning algorithms like a JRPO. So yeah, there is a direction that people are discussing, I think. Yeah. Okay.
Yeah, hi, super interesting talk. So I come from the hardware side of things, hardware design side of things. So in context of that, like one of the things that I wanted to understand is like a lot of the data that I train is fully private. In the sense, so in context of this specific training that you're doing, when you're using LLM as a judge, what kind of context you're recommending for, like, let's say, private data? If I want to apply this on my own private data, where I won't send it outside, but then I would probably use a foundation model for training. So then what is your recommendation for that?
So yeah, I think for LLM as a judge, it's important to have like the right abstraction of context that would be provided. For us, we basically use like the generated code and other generated code to provide context, and as well as like the initial plan and idea markdown that we used. You mentioned hardware design.
Like basically we have representations of the text in a sort of abstracted syntax tree, something like that.
I see.
So basically it's a structural representation. It's not like a sort of a linear code sort of thing.
I see.
So something like that.
I think if there is a way to kind of like summarize this like AST into like simplistic descriptions, and you could have like many such simplistic descriptions, and then I think you could kind of LLM can first like decide which one to optimize for, and then like once that's decided, like, you can have like expand that description just to kind of reduce the number of contexts, like a tokens, and I think that's something that can be done. Yeah. Yeah. Yeah.
Any more questions? Oh, you make me run all the way back to you, huh? Thanks.
Hello, thank you for the great talk. I had one question regarding the evaluation methodology where you were trying to basically get your AI Scientist-v2 to recreate pre-existing studies. How do you make sure that the studies that you are trying to recreate are not part of the training set of the LLM that is being used to try to recreate that study? Like, is that part of the consideration? And does that mean that, for example, frontier models that are being released today, we'll have to wait for like new research to come out to then subsequently replicate it in the future?
Yeah, so I think that depends on like basically how well the literature search part could be executed, and that's sort of like that itself depends on how well the underlying LLMs are good at like web search and doing this summarizing the existing literature search, also the summarizing the existing literature. So I think right now it's sort of like we like finding something that has been done in the past, but sort of like buried in the literature. That is like the most kind of difficult part. And I think maybe even last week there was an OpenAI like a GPT-5 was able to find some like addition, like problems solutions that were kind of buried in the literature, and they sort of like I guess it was sort of like a big thing in a sense that previous LLM weren't able to discover that sort of knowledge from the literature, even though the knowledge itself was there. So I think we would still see continued progress in that sort of like base LLM domain, and as we have more sort of like agentic LLM capabilities, we become more better. We will also try to. I think we can mitigate sort of like the rediscovering knowledge in this sort of AI scientist system as well. Yeah.